Okay, in this video, we're going to finally look at the relationship between work and really energy. It does focus around kinetic energy, but understand that this is also ties to all forms of energy. And so the amount of work done on an object is going to equal that object's change in kinetic energy. So this is what we know as the work energy theorem. Okay. In fact, if you look at some of the definitions between energy and work, right, they use each other in the formulas or in the definitions. So the way we write this is just that the amount of work done is equal to the change in kinetic energy, okay, which would then allow us to kind of expand this equation to be, right, net force times delta x equals 1/2 mass times v squared minus v initial squared, okay. You may need to use that relationship at some point in time. So there it is. It does make it a little bit easier here on the v squared minus v initial squared to put into your calculator, but also don't fall into the trap. They'll ask you a multiple choice question about what does work equal. And a lot of times students will select the option that says work just equals kinetic energy, forgetting that when you know, it's v squared minus v initial squared, right? They'll just say, oh, but the initial velocity is 0, so it just equals the final kinetic energy. That's true, right? Especially if you start from rest. But remember that work itself does not equal a specific kinetic energy. It equals the change in kinetic energy. Okay. So now let's just simply redefine work in terms of energy. So work is the process by which a force transfers energy into or out of a system, okay? This is where that positive and negative comes into play, okay? And so this is why work and energy are scalar quantities versus being vector quantities, right? So when we do positive work, right, it just means that energy is being transferred into a system, right? So I'm increasing the energy of the system. If I do negative work, okay, that means I'm transferring energy out of a system. So I'm removing it. And then if there's zero work, right, or no work done, there's simply no energy transfer, okay, between the two. So just remember that each force acting on an object will perform work and is the means by which energy is transferred, okay? Now, something like an applied force. Right, an applied force would apply positive work, right? Because we're going to be moving in the positive direction. That force is going to cause a positive change in motion. However, something like friction, for the majority of cases, will do negative work, right? It's removing energy from the system. Okay, so here the applied force would transfer in, right? Here, friction would transfer out. When we say transfer, we're talking about the energy. Okay. Now let's look at a quick example here where we use this work energy theorem. And very typical, they're going to give you like force and distance, ask you to find maybe a final speed. They're going to give you all this information for speed, ask you to find work done. Okay. So here you got two questions. A car of mass 2,000 kilograms speeds up from 10 meters per second to 20 meters per second. What net work is done on the car to increase its speed, and then what net work is done to accelerate the car from 20 to 30 meters per second. So they actually want you to fall into a trap here, because if you look, right, the delta V's is 10 meters per second for both situations, right? But you do have to be careful, because that's not the V that we're not doing delta V, okay? We're doing actually delta V squared, right? And so that means the difference of, right, the velocity squared. So we just simply use our equation. So work equals 1/2 mass times v squared minus v initial squared. So for the first situation, it'd be 1/2 times 2,000 times 20 squared minus 10 squared. Okay, and so once we do our number, we find that we are going to transfer in 3 times 10 to the 5th joules of energy. Right? How do we know we're transferring in? This number ended up being positive. If you actually look, we're speeding up. Okay. Now for the second case, we're going to use the same equation. Work use 1/2 mass times v squared minus v initial squared. Okay. Same car, so it's still 2,000 kilograms. Now we're going to go 30 squared minus 20 squared. Yes, the change in speeds is 10, but remember, we're squaring the speeds, the individual speeds, then subtracting. So in this case, we're going to have to add, or we will add in 5 times 10 to the 5th joules of energy, right? Again, we're adding, we're increasing the energy in the system because we're speeding up, okay? Now, in the next video, we're going to add a little bit more calculus into this. We're going to talk about the dot product and how does work, behave in this dot product manner. But that's going to be our next video, and then we'll do a little bit of variable forces after that.